So Chem 123, and our first unit, or unit number 1, is going to be titled Solubility. So we've heard this term solubility before. And where that came up, it came up in chapter 4 of our textbook. And in chapter 4, it kind of gave this vague definition of solubility, and it was more like a black and white definition. We either say a substance is soluble or it's insoluble, and there's no in between. In reality, that is a very, very broad generalization, because there is a whole range of solubility. So we need to kind of formalize a better definition, because we can calculate just how soluble or how insoluble a particular salt is. So in Chemistry 121, we came up with something called solubility rules. And like I said, we can classify something as soluble, or we can classify it as insoluble. In reality, and what we're going to be doing here in Chem 123, is there's more like a continuum of solubility. So this is what we're going to investigate right here. So when we discussed solubility rules in chapter 4, we did that in a qualitative sense, which means you can just identify something in a type of black and white manner, and we don't really care about the amount. We asked the question, is something present, yes or no? In this case, we asked, is a solid present in solution, yes or no? And we can easily categorize that. But as you found out in lab this week, experimentally, we can consider solubility equilibria to make predictions about the amount of a given salt that will dissolve. So there's a couple of key things that I want to point out about this statement. We use the term equilibria, and then also the term amount. We can actually determine how many grams will dissolve per liter. And we can look at the equilibria and use the terms and use the equilibrium expressions that we looked at in chapter 15, 16, and 17 to continue to analyze solubility. So typically, you have a generic salt, we'll say in this case A, X2, as a solid. It's going to be in equilibrium with ions in solution. In this case, we can have A plus in aqueous solution plus 2X minus also in aqueous solution. As chemists, we can now evaluate this equilibrium expression. We can see how far this equilibrium will lie to the right or how far the equilibrium will lie to the left. We've seen equilibrium constants before. I can rattle them off my head. There's Ka, there's Kb, there's Kc, there's Kp, there's Keq. We're now going to introduce a new type of equilibrium constant that deals with solubility. One thing that we want to remember, if we have a large value for K, that tells us something. If our value for K is very large, that means that the products are going to be favored. Or another way we can say that is that the equilibrium lies to the right. So if we have a very, very large value of K, what can that tell us about solubility? if our equilibrium lies to the right, that means we're going to have a lot of ions in solution. So if we have a large K, we would say there's going to be more ions in solution than there are solid. So that means that a particular salt will be very, very soluble. If we have a small K, that means that reactants are going to be favored. If the reactants are favored, the equilibrium is going to lie to the left. If we have reactants favored and a very, very small K, that means we're going to have more solid. So our particular salt is going to be more soluble or it's going to be more insoluble or less soluble. Okay? So make sure you think about the magnitude of your equilibrium constant K when you're looking at these particular salts dissolving.